Interviews are supposed to be difficult. If you don't get every or any answer immediately, that's okay. That's the normal experience, and it is not bad. Listen for the guidance from the interviewer. The interviewer might take a more active or less active role in your problem solving. The level of interviewer participation depends on your performance, the difficulty of the question, what the interviewer is looking for, and the interviewer's own personality. When you are given a problem, work your way through it using the approach below. So, first approach I need you to understand is listening. So, listen carefully. You've likely heard this advice before, but I am saying something a bit more than the standard. Make sure you hear the problem correctly advice. Yes, you do want to listen to the problem and make sure you heard it correctly. You do want to ask questions about anything you are unsure about. But I am saying something more than that. Listen carefully to the problem and be sure that you have mentally recorded any unique information in the problem. For example, suppose a question starts with one of the following lines. It's reasonable to assume that the information is there for a reason. Given to arrays that are sorted. Find, for example, and etc. You probably need to know that the data is sorted. So the optimal algorithm for the sorted situation is probably different than the optimal algorithm for unsorted situation. Okay? So it's unlikely that your interviewer would give you this information if it didn't affect the algorithm. Okay? Your first algorithm does not need to use the information. But if you find yourself stuck or you are still working to develop something more optimal, ask yourself if you have used all information in the problem. So be patient and listen carefully. The second advice in the problem solving flow chart is draw an example. An example can dynamically improve your ability to solve an interview question. And yet, so many candidates just try to solve the questions in their heads. When you hear a question, get out of your chair, go to the whiteboard, and draw an example. Okay, so we have solved a bit, and we solved the exercises in the previous section about the big O notation by drawing and taking an example of every algorithm in order to know the big O notation. And later on in the arrays and the data structure and the algorithms, we are going to draw also an example on everything in order to get the design, the pattern, in order to get to know the algorithm, and in order to get what he needs to and what is the sequence that the program is following. The third step in a problem-solving flowchart is brute force. Once you have an example done, state a brute force. It's okay and expect that your initial algorithm won't be very optimal. Some candidates don't state the brute force because they think it is both obvious and terrible. But there's the thing, even if it is obvious for you, it's not necessarily obvious for all candidates. You don't want your interviewer to think that you are struggling to see even the easy solution. So despite being possibly slow, a brute force algorithm is valuable to discuss. It's a starting point for optimization and it helps you wrap your head around the problem. The fourth step is optimize. Once you have a brute force algorithm, you should work on optimizing it. A few techniques that work well are: look for unused information, use a fresh example, solve it incorrectly, and make time versus space trade off. Pre-compute information and use a hash table and think about the best convenience runtime. Walk through the brute force with these ideas in mind and look for the optimization. Walk through and approach. After you have nailed down an optimal algorithm, you don't just dive into coding. Take a moment to solidify your understanding of an algorithm. Whiteboard coding is slow, very slow. So is testing your code and fixing it. As a result, you need to make sure that you get it as close to perfect in the beginning as possible. Okay? If you don't understand exactly what you are about to write, you will struggle to code it. It will take you longer to finish the code, and you are more likely to make major errors. The sixth step is implement. Now that you have an optimal algorithm and you know exactly what you are going to write, go ahead and implement it. Start coding in the far top left corner of the whiteboard and avoid line creep. It makes your code look messy and can be very confusing when working with white space sensitive language like Python. Remember that you only have a short amount of code to demonstrate that you are a great developer. So everything counts. Okay? Now, the step number 7 is the test. You would not check in the code in the real life without testing it. And you should not submit code in an interview without testing it either. There are smart and not too so smart ways to test your code, though. Why? What many candidates do is take their earlier example and test it against their code. That might discover bugs, but it will take a really long time to do so. Hand testing is very slow. If you really did use a nice big example to develop your algorithm, then it will take you a very long time to find that little off by one error at the end of the code. What does this mean? Instead, trying this approach starts with the conceptual test. Okay, hotspot. Identify the hotspot like you have coded long enough to know that things are likely to cause a problem. Small test cases and special cases. Always try to optimize and solve techniques. Okay, so this is the flow chart of the problem solving. Recursion is a process in which a method calls itself continuously. A method that calls itself is called a recursive method. It makes the code compact but complex to understand. When you hear a problem beginning with the following statements, it's often, though not always, a good candidate for recursion. Design an algorithm to compute the nth, or write code to list the first n, or implement a method to compute all, and so on. Okay, so we use that for recursion. Recursive solutions, by definition, are built of solution to sub-problems. Many times this will mean simply to compute f of n by adding something, removing something, or otherwise changing the solution for f of n minus 1. And don't worry, we are going to make recursion as simple as like making any variable or adding two numbers. Yes, trust me. So, in other cases, you might solve the problem for the first half of the data set, then the second half, and then merge those results. For example, in Recursion, we have this. For example, we have this function called P and contains system.out.print hello and P, it's calling itself. And the public static void main, this is the main function that is in Java. It is executed during the runtime. So when you when you run the program, the function main would be executed. So function main is executed, so it will call P. So it will go up and call method P. So P would be executed now. It will print at the first line, hello. It will print hello. This is the think about it as and the output. It will print hello in the console and moves down to the second line. Second line is the recursive way, the recursive call of the method. It will call P. So it will go up and calls P. P is then being executed and called. So system.out.print, it will print again hello. It moves down here to P, and P, it will call the method. So again, it will go and call P, and it will print hello on the console. So hello would be displayed. And going down, and so on, P again and again. So this P, this writing, or this code will result in infinite loop. So infinite loop of hello. Okay? So this is the recursion. This is one of the bad things that may happen to you is the unlimited calling of the method. So you need a stopping condition to limit this recursive calling of the method. Okay? This is a quick example about the recursion. Let's take another example about recursion. We have now a method P and the main method. Main method is calling P. So P would be called above. We have created a count 0, integer count 0. When you call P, go and increase count plus plus. So count now, it's not 0, it is 1. If count, which is 1, is less than or equal to 5, go and do this. Yes, it is less than 5. So it will print hello. So this is the console. And it will print hello plus the count. Hello, count is equal to 1. Okay? And this will call again the P. So it will increase count plus plus. It will become 2. If count less than or equal to 5, yes, 2 less than or equal to 5, then print hello, hello, 2, and it will again call P. So P, it is called again. P above, being executed, count plus plus. So count would be now 3. 3. If 3 less than or equal to 5, yes, go and print hello. So hello, 3. And P, execute this. Call the method P. Again, it will increase the count by 1, so it will become 4. If count 4 less than 5, yes, system.out.print hello 4, and go down to the P, going up and call the method again, increase the count, become 5. 5 less than or equal to 5, yes. So system.out.print hello, count, hello, 5, and then call the method P. Again, go up and call it. Increase the count by 1. Count increased and becomes 6. 6 less than or equal to 5? No. So stop doing this. This program will result in 5 messages, hello 1 to till hello 5. So this is the stopping condition. Count, the count. So count plays the role as a limiting behavior, a limiting variable that will detect how many times the recursion will occur. Okay? In the next video, we are going to discuss the recursive versus. So what is the difference between recursive and iterative? Recursive algorithms can be very space inefficient. Each recursive call adds a new layer to the stack, which means that if your algorithm recurses to a depth of n, it uses at least O of n memory. For this reason, it's often better to implement a recursive algorithm iteratively. All recursive algorithms can be implemented iteratively, although sometimes the code to do so is much more complex. Okay? So, on the left, we have val x equal to f1, f2, f3, and return f3. So this is the recursive. f1 will depend on f2, f3, and then the returning of f3 will result in a calculation of f2, and f2 will result in calculation of f1. While in iterative, on the right, we have a variable x, and this variable, through the iteration, we change it from 1 to 2 to 3. So this is the iteration. We have a space, one space for a var x, while on the left, when we use recursion or recursive algorithms, we have to make a lot of space. So every time we are calling a function or need anything or need a new calculation, we are reserving a new space in memory. So you can structure your program to be tail recursive to make the compiler optimize and treat it as an iterative call. Okay, we have 3 functions. Imagine that we have 3 functions, A, B, and C. Function A calls function B, and function B calls function C. If function A returns the value of function B, and function B returns the value of function C, the instructions can be classified as tail recursive call, as the first and the top of this picture indicates. So this is the tail. If you don't need any variable to store function A and if you don't have or you don't need any variable to store function A and function B, function C does not need to return to function B. So this is the case in below. So when you have if you don't need any variable to store function A, this is function A, and function B calling f of B calls f of C, and f of C returns C. And when returning C, do something. When doing something, it will return B. So you just skip function B and function A and reuse the variable that A and have B and B have. Okay? So this is a bit about recursive versus iterative. Okay? Don't worry if you don't understand these concepts. In the next exercises, we are going to demonstrate the complexity of a recursive and it.